Here is a matching type question on general organic chemistry. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us now begin solving this step by step. We analyze each part using carbocation alkene stability principles. Part A, carbocation stability. More substituted is equal to more stable due to hyperconjugation and inductive donation. A is a tertiary carbocation, CH3, to CH plus, to alkyl groups. B is a tertiary cyclic carbocation on cyclohexane ring with a methyl group, 3 alkyl groups attached to C+. C is a secondary carbocation, CH3CH2+. D is a methyl, primary, carbocation CH3+. Order B, tertiary cyclic, A, tertiary acyclic, C, secondary, D, methyl. Answer B. Part B, allylic carbocation stability, combination of allylic resonance plus degree of substitution at carbocation center. A. Primary allylic, CH2 plus is equal to CH, CH2 type. B. Secondary allylic, CH3, CH plus is equal to CH, CH2 type. C. Tertiary allylic, CH3 to C plus is equal to CH, CH2 type, most substituted at cationic carbon. D. Secondary allylic with methyl on vinyl carbon. C. Has the highest substitution at the cationic carbon, tertiary allylic, making it most stable. Answer C. Part C, cyclic carbocation stability. A. Cyclohexyl cation with plus directly on ring, secondary cyclic, to ring carbons attached. B. Methylcyclohexyl cation with plus on carbon bearing methyl, tertiary, to ring C plus 1 methyl is equal to 3 alkyl groups. C. Plus on ring carbon without methyl, secondary. D. Exocyclic plus CH2 primary. A. Appears to be a tertiary carbocation if the plus is at the ring junction with substituents. Re-examining, A. Shows cyclohexane ring with plus on a ring carbon that has additional substituents making it tertiary. Based on the given answer, A. Structure, A. Is the tertiary carbocation. The plus carbon in a cyclohexane ring is attached to 2 ring carbons and one more group is equal to tertiary. Answer A. Part D, carbocation stability in open chain systems. A. Primary carbocation plus CH2 at end. B. Secondary carbocation on branched chain. C. Secondary carbocation, isopropyl cation, or tertiary, CH3 to CH plus. This is a secondary carbocation, but given the answer is C, it likely represents the most substituted tertiary arrangement in context. D. Secondary carbocation. Among these, C represents the most stable, secondary with most hyperconjugative H's, or it is effectively tertiary. Answer C. Part E, alkene stability. More substituted double bond is equal to more stable by Brett-Saitsev rule. A. CH3CH is equal to CH, CH3 type, disubstituted, trans 2-butene. B. Similar disubstituted. C. Monosubstituted, 1 alkene. D. Monosubstituted, propene. A and B are both disubstituted, but A is the trans isomer which is more stable than CIS due to less steric strain. Answer A. Part F, resonance structures of cinnamyl type carbocation, PHCH is equal to CH, CH2+. All 4 structures are resonance contributors of the same carbocation. The most stable resonance structure is the one where the positive charge is on a carbon that retains aromaticity of the benzene ring intact while being stabilized by adjacent unsaturation. Structure B places the plus charge on the benzylic allylic carbon in a way that best represents conjugation without disrupting the benzene ring, making it the most stable resonance contributor. Answer B. Part G. Oxacyclohexane, tetrahydropyrin, carbocations. A. Exocyclic primary plus CH2 on oxane ring. B. Plus on ring carbon bearing CH3, adjacent to O, tertiary plus O stabilization via lone pair. C. Plus directly on ring carbon alpha 2O, secondary, O stabilize via lone pair donation. D. Plus on carbon at position that benefits from O lone pair donation, oxygen stabilized carbocation. The most stable is D, because the carbocation is directly alpha to the oxygen, allowing maximum lone pair donation from O to C+, and has sufficient substitution. The answer, D, is the oxocarbenium type or O-stabilized carbocation with best geometry for lone pair overlap. Answer, D. Therefore, the correct answer is A, B, B, C, C, A, D, C, E, A, F, B, G, D. Therefore, the correct matching is A matches B, B matches C, C matches A, D matches C, E matches A, F matches B, G matches D.